Okay, so here we're going to pull together all the things that we've been using here. It says it in the notes. We're going to take a polynomial and we want to find each of the roots, and we want to classify them as integer, rational, irrational, and non-real. First one we want to use is the rational root theorem, or gives you the possible rational roots. The remainder theorem and the factor theorem, those two are linked. And then synthetic to Horner's algorithm. Then when we're done with that, we'll have to use quadratic formula or factoring. So first thing we want to use is the rational root theorem, which takes the factors of the constant term, which is plus or minus 1 and plus or minus 3, and divides it by the factors of the lead coefficient. So this is just plus or minus 1 and plus or minus 3. So now we're going to use the remainder theorem / factor theorem. Pretend I wrote factor theorem there. And we're going to evaluate the function at 1, -1, 3, and -3. Again, the whole purpose of this is to find the roots. So we want to hopefully get a couple of values here that are equal to 0. So let me plug it into the calculator. Here's our polynomial. So using the table values, let's clear out what I have in there. We want to do 1, -1, 3, and -3. So we get -28, 0, 0, and -60. So -28, 0, 0, and -60. So clearly, this one is helpful as well as this one. So again, the whole purpose is to find the roots. Since we have two rational roots, 3 and -1, hopefully we can take this 4th degree polynomial, which is going to have at most 4 roots, that we can find the other 2 roots after we use this. So since synthetic division will reduce in degree by 1, since this is a linear factor and this is also a linear factor. So if we do with one after another, our 4th degree will go from 4 down to a 2nd degree, which is a quadratic, so a quadratic formula or factoring will come into play. So I want to take 3 and divide it into this using synthetic division, because synthetic division is so much easier than long division. So synthetic division, bring down the 1, add, I get 6, 18, 6, 18, 1, 3, 0. So since I've chosen 3, I don't need to do it again. I'm now going to do -1. I'm going to divide -1 into this, and hopefully it'll reduce our function. So now it's a originally it was a quartic, now it's a cubic. After I do this synthetic division, I should have a quadratic. So I bring the 1 down, -1, 5, -5, 1, -1, 0. So now I have a quartic, a cubic, now I have a quadratic. So let's just change our color. So now we have x squared, x plus 1. So I now have x squared plus 5x plus 1, and now I'm going to set that equal to 0 to find the other roots. So I already have 2 of the roots. I'm going to hopefully get the other 2 out of this right here. Well, whenever we have a quadratic, the first thing we want to consider is factoring. Can I factor this? No, there's no factor of 1 that give me 5. So I'm going to use the quadratic formula. Again, the quadratic formula is only used if you cannot factor. All over 2. So this is -5 plus or minus the square root of 25 minus 4 all over 2, which is -5 plus or minus the square root of 21 over 2. And this is an irrational root, and 3 and -1 are integers. Just want to make a note here that I chose 3 first and then -1 second. It doesn't matter which order I do it in. So let's just try doing it in a different order. Whoa. So here are the coefficients of the quartic again. As opposed to doing 3 first, I'm going to do -1 first. So I bring down the 1, I get -1, 2, -2, -14, 14, -3, 3, and 0. And now I'm going to divide 3 into it. So I get 1, and then 3, and 5, and 15, and 1, and 3, and 0. Notice that my final quotient is 151, 151. So I got the same thing regardless of which order in which I did it. Okay. So what are the x-intercepts, or what are the roots of the polynomial? There are 4 of them. 3 and -1 are the integer ones. Since the square root of 21 cannot be simplified, I think I just put a little mark there. The square root of 21 can't be simplified. It's an irrational root. So we have 4 roots. 2 are irrational and 2 are integers. So let's try to find the roots of our polynomial again. First, I'm going to use the rational root theorem. Factors of 4, which are my p-values, are ±1, ±2, and ±4. And my q-values are ±1, ±3. I then divide 1 by both of these, so I get ±1 and ±1/3. 2 by both of those, I get ±2, ±2/3, ±4, ±4/3. And then I'm going to evaluate the function at these 2, 4, 6, 8, 10, 12 values. Let me write those. Okay, so I have my function plugged in here. Again, I go to table set. I don't care what the starting values are. I just want to make sure my independent or x values is on ask. I go to my table, and then so we do 1, -1, 1/3, -1/3, 2, and -2, and 2/3. So we want to write down all those values there, and then go back up to the top, delete what you have, and do the rest of them. So you can imagine that I just did those all out. So let me write out the answers. So here's the root. Here's using the remainder theorem / factor theorem. I don't know why there's an E there. The only one interesting is this one right here, because that's the one that gives us 0. So therefore I'm going to take this cubic, divide it by 1/3. So I get 3, -1, 12, -4. So 3, -1, mistake, 0, 0, 12, 4, 0. So this is a cubic. I'm dividing it by a linear. I get 3x squared plus 12 is equal to 0. Since there's only 2 terms, I can just solve this like a linear. And I can isolate the variable. So this is -12, x squared equals -4, x equals plus or minus the square root of -4, which hopefully you know is plus or minus 2i. At this stage of the game, we're going to call it a non-real root, and we're going to call 1/3 a rational root. So we have 3 roots because it's a cubic. One of them is rational, 1/3, and 2 of them are complex, plus or minus 2i. So we have our 3 roots that we have. So using the rational root theorem, the remainder theorem, synthetic division, and then just solving a simple quadratic, we found the 3 roots that we have for this polynomial.